Holiday Resonant, Chapter 22, Problem 37. Suppose you design an apparatus in which a uniform charged disk of radius r is to produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk at a point P, at a distance 2r from the disk. Cost analysis suggests that you switch to a ring of the same outer radius r, but with inner radius r over 2. Assume that the ring will have the same surface charge density as the original disk. If you switch to the ring, by what percentage will you decrease the electric field magnitude at P? So first we're going to compute the electric field for a solid disk, this one, and then we'll do the one that has a donut hole. So first we know that dE, we're going to write our formula for electric field, is equal to 1 over 4 pi epsilon naught. We'll use this rather than K because we're going to have some pi factors that will cancel out, times dQ times the cosine of theta in this case. And we're getting that cosine from theta here. And at the edge, if we're all the way at the edge, we would have from here to here a charge, and that will be dE, but the distance, this is 2r. They gave us 2r for this to the point P, and they gave us r. This r is perpendicular. It's perpendicular to the 2r axis, which we're going to call Z. Just call that Z. And we're going to say this is running in the x direction. So what we have is 2r squared plus, we use the small r. This is the one that can go from 0 all the way to the edge, where r will equal r at edge. So we have r squared. Now, this cosine function, you've seen it before. What's happening here is, we're just going to take what's happening up here. For every charge, say on a ring, let's do it on a ring, there's a equal and opposite charge on the other side. So what happens is that, looking at the top of this ring, say we got and this is just the elemental section. So you have an equal and opposite charge on the other side, and it's going to add, E's going to add, you can see from symmetry, right straight along the Z axis. But these two, this charge here, straight from the elemental element to here, will cancel. They're going to cancel out. So we have no, in this case, we have no X component. We only have the Z component. And so we put theta here. The same as we did here. This is, I just tilted so we can, tilted this over so we can look at it a little bit better. Now we got the thickness for an elemental ring of this ring we made, and we call that thickness dr. Now dr goes all the way around, so essentially what we have is in a circle we have 2 pi r. That's this circle going all the way around, and we have a thickness of dr. So the area of this elemental ring is equal to 2 pi r dr. Now we also have a charge density on this disk that's uniformly distributed, and that's sigma is going to equal dq per area, and we are right now, our area is 2 pi r dr. So dq, this is going to go to dq equals sigma 2 pi r dr. So we look at our formula. We got one other thing left. We have the cosine of theta. We picked up that cosine. These are vectors, and to pick that cosine up from these two vectors here, and when we look at it, this is just 2r. So the cosine of theta is going to equal 2r over the hypotenuse, which is going to be 2r, and the hypotenuse is 2r squared plus r squared. So now when we put this together, we're going to have dE is going to equal k, which is 1 over 4 pi epsilon naught. We're going to use that form of it, times dq. But what is dq? dq is sigma 2 pi r dr, and that's going to be divided by, should have been up here, r squared. That's our formula for electric field. So we got r squared, which is going to be the square root of 2r squared plus r squared. And this whole thing is going to be squared times the cosine of theta. And the cosine of theta, which is going to be 2r over the square root of 2r squared plus r squared. So we can go with dE is equal 1 over 4 pi epsilon naught times sigma 2 pi r dr. This is squared, so what we're going to have is just 2r squared plus r squared, since we squared the square root, times the square root of 2r squared plus r squared, and that's going to give us 2r squared plus r squared to the 3/2. This is 1 once you square it, and this is 1/2, which gives you 3/2. And also we had 2r, we'll put that here, almost left it out, just put it right over here, 2r. So we can begin to sum up all these. So to sum it, we're going to have E, well, let's just write it in, it's going to equal integral dE, which is going to equal, since we kind of know we can pull the constants out by now, let's pull out our constant. 2r is a constant. It's fixed. It's just this from the center to the point, and it does not change 2r, so we can pull it out. 2r. We know the charge density is fixed. It's the same. It's uniform throughout the disk, so we got sigma. And also 2 pi is a constant. And we can put all that over 4 pi epsilon naught. And so that's pulled out of the integral. So then we got the integral of r dr over 2r squared plus r squared to the 3/2. Now we can make some simplifications. We can get rid of this 2 pi and this 4 and change it to 2. Now you may be tempted to want to do take this 2 to 1, but let's leave this as 2r because that's the length of the from the center to the point. So we'll leave that as 2r. And right now we're going to do a u substitution for this integral. You probably can look it up if you like, but I'm going to do the u substitution, which is something we easily can do. So we're looking at, you look at this part here and you say u is equal to 2r squared plus r squared. You don't need to pay any attention to the 3/2. So that's u. So what is du? Well, du is 2r dr. That's equal to du. And when you look at that, you got r dr. That's the form you want that in. So this will go to du over 2 equals r dr. So with these change in variables, we're going to have a change in the limits. Before, it was just from 0, center of the circle, to r, to the edge of the circle. That's the limit. Now for u, this is what we have to do. When r is 0, right at the center of the disk, u, when r is 0, u equals 2r squared. And when r is r, the limit u, this equal 2r squared plus r squared. Those are, so we have sigma 2r over 4 epsilon naught integral 2r squared to 2r squared plus r squared du over u to the 3/2. Now that became a 4. I don't remember what I told you when we had du over 2, and then 2 times 2 made this a 4 out here. And that will equal, let's just go to sigma 2r over 4 epsilon naught integral 2r squared, 2r squared plus r squared. And bring this up, I have du to the u 3/2, the minus 3/2. So when we do the integral, we're going to have sigma 2r over 4 epsilon naught, and we're going to have u to the minus 1/2 divided by minus 1/2 with 2r squared to 2r squared plus r squared as the limits. So we have sigma over minus 2 epsilon naught, just took that out, and we have limits of 2r squared to 2r squared plus r, and that is 1. This comes, it's a minus 1 that comes in the denominator. So it's going to be 1 over square root of u, and we're going to plug it in what u is. U is 2r squared plus r. So we're going to plug in u, which is 2r squared plus r minus 1 over the square root, the lower limits, 2r squared, and we had sigma 2r here. And we're going to distribute this 2r across here. So we can do that now. We just put it, we got 2r here and 2r here. And we got a minus sign here. So we can switch the order of these two. So we have sigma. Sort of look like the formula you're used to seeing. 2 epsilon naught times, this is switching, so that's 2r over the square root of 2r squared minus 2r over the square root of 2r squared plus r squared. So now that we have that, we can begin to solve this equation. Let's do this step real quick. Sigma over 2 epsilon naught times, well, 2r squared is the same as, I'll write the whole step out, 4r squared. When you square this whole thing, that's 2r squared. So we got 4r squared, this in your square root, over 2r minus 2r over the square root of 2r squared, which is going to be, if we square it, we're going to have 4r squared. And this r is the same as r. It's already at the end, so we just say plus r. And this is going to go to sigma over 2 epsilon naught times 2r. We can take that 4 outside and it'll just be 2 r squared, which is 1, minus 2r, and this is 4r squared. We squared that, and this r is the same now as r because it's all the way at the end of the limits. So where r becomes r, and so we have 4r squared plus r. So we got the square root of 5r squared, the square root of 5r squared. Then we can take the r out, and we're going to have r is equal to square root of 5. So, so we have r square root of 5. These r's cancel. And this becomes 1. So let's just rewrite it. So we have sigma 2 epsilon naught 1 minus 2r over the square root of 5. So that's the expression for A. That's just 2 over the square root of 5 that are canceled right here. So that's for A. Now B is going to be very similar, and so we're going to kind of speed this up. U for B is 2r squared plus r over 2. And du is going to equal and this is squared. So if we squared that, I just want to show you this. That'll be r squared over 4. And then when we go to du, it's going to equal 2r dr, and that's over 4. So that's going to equal r dr over 2. That's du. So du is going to equal r dr, and so that's du which goes to du over 2 equals r dr. So now we can use some of the same formulas that we developed before without doing all the work. So we're going to have sigma 2r, that doesn't go anywhere from the before, over 2 epsilon naught, and we're going to have limits again. When this is 0, we have 2r squared. And at r, we have 2r squared we have 2r squared plus r over 2 squared, and we're going to have du over 2 again. We're going to take that out and make that a 4. And we're going to have times 1 over u to the 3/2. That's this u. It only changed a little bit for the, this is the one, this is B. We're working the situation where we have a hole in it of r over 2. So this is B. So here we have sigma 2r. We're just keeping it together because that's the length from the center to the point. And I'm going to take this 2 on out and make that 4 epsilon naught. And we're going to go, just write this down like this one more time. 2r squared, 2r squared plus r over 2 squared, and it's going to equal du. And I'm going to bring this u up, and that'll be u to the minus 3/2. So we're going to do this integral. And since we've done it before, very close to it, sigma 2r over 4 epsilon naught, and that's going to be from 2r squared to 2r squared plus r over 2 squared, and this is going to be u1 over, so when you take that 1 from that, you get a minus 1/2, so that'll put that in the denominator as just the square root of u. And then you have another minus 1/2 that'll be in the denominator that will come over here, and it's minus 1/2 times 4. So we're ready to go. So we have sigma 2r divided by minus 2 epsilon naught. The minus 1/2 came from doing the integral. And we have 2r squared plus r over 2 squared, and we have 2r squared here. So putting this in 1 over the square root of 2r squared plus r squared minus this limit, which is going to be 1 over the square root of 2r squared, and we're going to distribute this 2r. So we got that we did before. So 2r, and here's the same thing, 2r into our equation. And now we have sigma, and if we multiply by this minus 1, that'll just switch the order again. It will have a 2 epsilon naught, and we're multiplying everything through by minus 1. So we're going to have 2r over the square root of 2r squared minus 2r over the square root of 2r squared plus r squared. And we can clean this up a little. We got sigma over 2 epsilon naught. Now this is just going to be 2r, and when you square that, you're going to get 4r squared. 4r squared. You're going to take the r out, and this is what you're going to have. You're going to have r, and the square root, that's 4r squared, so you can take the 2 out. This is a perfect square. So you got 2r over 2r, just like before, and that's going to end up being 1, minus, so in the numerator, we still have 2r. Now let's look at this. When we square that, we got 4 r squared plus r squared over 4. So if you got 4r squared and r squared over 4, that's 16 over 4 r squared plus 1, because this r goes to the large R again, plus r over 4 will give you 17 over 4 r squared. And as before, we're going to take that r out, square. That'll cancel this. So what we have here is sigma over 2 epsilon naught 1 minus 2r over this 2, we canceled r's, over the square root of 17 over 4. Now the problem asks for the percent difference. And we state percent difference as, now to answer the question, we know that the percent difference, EA minus EB is over 2A, and they're going to multiply that by 100%. So EB is equal to EA minus this right here, sigma over 2 epsilon naught 1 minus 2, that's just 2, over the square root of 17 over 4. Now, we've got EA minus EB. So if we go EB minus EA is equal to minus, we don't have to bother with this constant here. So we're just going to go with 1 minus 2 over the square root 17 over 4. Multiplying through by the constant don't change anything. So in both cases, they have this constant, the same constant. So we're just going to dispense with that constant for now. And if since I need EA minus EB, to change that, I'll just multiply EA minus EB. It's just going to equal 1 minus the square root of 2 over 2 divided by the square root of 17 over 4. So that's EA minus EB, and that's just going to be divided by 2EA. I don't know what I'm thinking about. Must be that's EA, not 2A. So divided by EA. So here we go. We have EA minus EB over EA is going to equal, we got this part, 1 minus 2 divided by square root of 17 over 4 divided by EA, which is sigma over 2 epsilon naught. We ignored that because that would multiply through in both cases, so we don't have to worry about this constant. So it's going to be divided by EA, which is 1 minus 2 over the square root of 5. And when you do that math, which equals 28.3%. Thank you.